My name is Doug Gobeille. I am a teaching professor here at URI. I've been here for about 10 years. My primary research is in high-energy extragalactic radio astrophysics, primarily studying supermassive black holes in the most distant galaxies that we can see. That work is primarily done with radio waves using the Very Large Array in Socorro, New Mexico, as well as the Chandra and Fermi space telescopes. Everyone's interested in space. On that front, it's easy. It's the difference between, I literally joke that if you say, what do I do? If I say astronomy, you are interested. If I say astrophysics, probably less so. And it's the idea that that physics word is in there. And I think most people, space is one of those few places where even the kind of most curmudgeonly adults can still go, oh, that's pretty cool, and be readily pulled in. And as we're looking at the future of astrophysics and physics at URI, when I came here in 2014, which seems so long ago now, at this point, basically it was just the classes. There really wasn't astronomy research going on. And now we are bringing in just as much money frequently, if not more papers. We're really competing with the other well-established research groups, which I don't want to sound bad with that. It's, again, we're all kind of working together, but it's just gone from literally nothing to something that is, I show my age, I always feel like Mighty Mac. We're out punching our weight class quite a lot here. And it's just exciting to see that because there's growth here. We are here to kind of enthrall human imagination in so many ways, to keep people thinking, to keep people humble. I grew up watching Carl Sagan on WGBH PBS Boston, Channel 2, and wrapped around my TV watching Cosmos back in the early 80s. And I have the same objective in many ways that Carl did in terms of him talking about things like the pale blue dot. Everyone's here on this one tiny little rock together. I try and say, let's not ruin it. We're all on the same bus together. It's not as big of a bus as we think it is. It's stuff like that is the best I can do. If I can keep inspiring imagination and creativity, that's a win.
Good afternoon, everyone. My name is Karen LaPointe, and on behalf of the URI Foundation and Alumni Engagement, I'd like to welcome you to our program today. We're happy to present our first Faculty Office Hour discussion for the spring semester. We're continuing our celebration of the 75th anniversary of the College of Arts and Sciences by visiting two science professors this semester. Today, we welcome Doug Gobeille, teaching professor of astrophysics. Moderating the discussion is Mary Beth Riley-McGreen, a digital content strategist in URI's Department of External Relations and Communications. If you have questions for Professor Gobeille today, please post them in the Q&A section on your screens, and we'll do our best to get to as many questions as we can after the presentation. And just a quick note, today's program is being recorded. In a few days, you'll receive an email with a link to the recording, along with recommended resources for further reading. You'll also be receiving a very brief survey from us, and we do welcome your feedback. Now, I'd like to invite Mary Beth to introduce Professor Gobeille.
Thank you, Karen. Welcome, everyone. I am so happy to be here and so glad you could join me in becoming enthralled. Today, I'm pleased to introduce you to Doug Gobeille, teaching professor of astrophysics, who has been at URI for almost a decade. His classes examine life, humanity, and their place in the universe by incorporating modern observations and publications into introductory classroom investigations. A separate team-taught course, Professor Gobeille teaches investigates science in science fiction media with a focus on film and television. Professor Gobeille also works with other faculty to build the overall astronomy and astrophysics facet of URI's Physics Department, including undergraduate research, upper-level courses, and astrophotography. Professor Gobeille's primary research focuses on the study of supermassive black holes, specifically their production of active galactic nuclei and their evolution through cosmological time. This research builds on his undergraduate work with Dr. Leslie Brown at Connecticut College and graduate studies with Dr. John Wardle at Brandeis University. And now I'd like to invite Professor Gobeille to join me on screen for today's presentation.
Hi there.
Hi. All right. I expect a lot of questions from the audience, so I'm just launching right in.
How about
Black
it?
holes, what are they, and should we be afraid?
Black holes, we'll start with no. Generally, almost never we should be afraid at this point in time. Perhaps in the future, under really bizarre circumstances, maybe, but no, not in general. They're kind of hyped up. Black holes in general, by their simple definition, are going to be something that is massive enough to collapse itself into a small enough state where light can't escape it if it gets close enough. This kind of tells us in a loose working definition that a black hole has nothing to do with mass really at the end of the day or size. We can have black holes that are some of the most massive things in the universe. That's what I say, supermassive and ultramassive black holes. These are millions or billions of suns worth of material. But they could also be very small. If I took anything that you had, if I could crush it down hard enough, it would eventually be dense enough that it has enough gravity around it that light is going to be unable to escape. We have a lot of ideas of infinities that are floating around with black holes, like infinite gravity. No. Infinite mass. No. Infinite volume, that gets a bit deeper, literally, and pun intended. But we'll probably eject there.
Um, so supermassive black hole. Why can you explain that distinction a little bit? Because I think black hole, I think massive, but when to say massive and then add super as an
Yeah.
additional qualifier, I'm like, I can't even kind of conceive of what that is.
Generally, when we do this in science, caveats abound, we mean it. So when we use that, we classify black holes into four categories. We have the largest, which are supermassive black holes, millions to billions of suns worth of material. To kind of level the playing field, galaxies like the Milky Way, off the top of my head, are about 1 trillion solar masses and change. So it's not like we're really talking about the majority. If we say there is a supermassive black hole at the heart of the Milky Way galaxy, Sagittarius A star, it has a mass of 4 million suns between friends. And that is nothing, absolutely nothing in comparison to the overall mass of the galaxy itself. So again, it's not this huge thing that really bothers the whole thing. It's critical. It has a lot of roles that it played, especially early on. There's a lot to be said there. Those are the biggest ones. We get to go to intermediate mass black holes. They're a bit weird because we're just kind of finding them and starting to better understand them. These are on the orders of thousands to millions of suns worth of material. You have stellar mass black holes. That's what most people are thinking about when they think about black holes. We have joked before in our discussions, the 1978 movie, The Black Hole from Disney. That's what they were kind of working with there. That's what people have in their minds, especially these sucking things in, which black holes are absolutely terrible at doing. And we can talk about that in a minute. But these are going to be black holes, a few solar masses, like 3 suns up to a few hundred suns, which again, as an astronomer, just a few hundred stars. Small, really, in the grand scheme of things. There are, we know of stars that have masses upwards of about 265 to 300 solar masses right now. And while black holes can get bigger, they're on the competing size scale at that point. And then we've got primordial black holes, which are going to be bitty. They could be, again, casually say, the size of mountains or smaller. And so it shows us again, it's not really about size, and it's not really about mass. It has everything to just do with the density of whatever it is. And you just need the circumstances to collapse that thing in to form it. And all of these are formed in different mechanisms, though are likely related to each other on some ways. The primordial ones are kind of off on their own. I say that and my brain starts going, maybe making linkages, but they are generally related. But again, we can break them up into groups. It's just how much mass you have. Humans like to draw lines. That's all we've done here. We have a whole spectrum of almost no mass at all to some of the biggest single objects we really know about. And so we tried to group them.
So one thing we should probably establish at the outset is that we're going to be having a lot of theoretical discussion today, because experiential learning in space isn't really available to that many people. So in the spirit of conjecture, I fall into a black hole. What
first, I would be clear that someone truly really doesn't like you, as I like to say, because throwing you into a black hole to kill you or to remove you from existence is very time and labor intensive, to put it bluntly. There are so many easier ways we could go about this. So you must have done something very fascinating, because the first thing we need to consider is that all black holes, most black holes, are going to be spinning, and probably spinning rather rapidly.
Mhm.
This is going to be very much like an analogy here. If you have an old, you go to an old batting cage, you just have a big wheel that's spinning really fast in the pitching machine, and we just drop a ball onto it. The ball hits the spinning wheel and boom, right out the front in the direction of the spin of the wheel.
Mhm.
You're the ball and the wheel is the black hole. Your odds of going in are terrifyingly low. I would have to send you in very fast at a very well thought out angle to try and make this all happen. As we just kind of alluded to a moment ago, black holes are actually kind of terrible at eating things. We joke that they are incredibly messy eaters. Like small children, kind of more doesn't go in the mouth than does go in the mouth sometimes. And the reason for this is in part because of that spinning, but also because of the insane tidal forces that you're going to be feeling at these points. As you get closer and closer, we don't notice tidal forces generally on Earth from Earth, because Earth is about 6,400 kilometers across. We want to say 6.4 million meters, and you're about one. So the gravity at your feet is higher than the gravity at your head, but it's so markedly small that you don't notice it. But
Mhm.
with a black hole, we can get much, much closer. If we crushed Earth down to a black hole, I think it's about the size of a peanut off the top of my head. And so we can get a lot closer to that peanut than we can to this Earth,
Mhm.
because as soon as you start going into Earth, other things arise. And so that means I can get close enough where the gravity I feel at my feet is immensely larger than the gravity I feel in my head. And this is going to start trying to pull me apart. This gets to this famous idea of death by black hole is spaghettification, where we just kind of pull you apart into one long string of the atoms and molecules of what you once were. That's where this messy eater business comes from. They shred everything that is going to try and get close to them: stars, people, asteroids, whatever it would be. And a lot of it will just be sent out elsewhere into space. And this is actually a really good thing, because black holes being messy eaters helps to spread the heavier elements of the periodic table out into cosmos. And if not for that, we wouldn't be here having the conversation today. So I'm
Mhm.
always quick to say, if we had this a reality that linked up with a lot of people's vision of black holes being incredibly, these vacuum cleaners eating everything around. One, as I like to say, you'd probably be inside of a black hole right now. Two, there
Mhm.
wouldn't be a lot of that material left. We actually need them to be mass eaters. They fling all this necessary material out from around them back out into space. They've enriched it to go from lighter elements to heavier elements, and they can fire that off. And again, that's where a lot of the iron and other heavier elements that are inside of us comes from. Not all, but a good chunk of it.
Mhm. And I just want to underscore, you said death by spaghettification.
Yeah.
That
uh, Definitely
is
not
the
my term,
scientific
but
term.
it is spaghettification, because we're effectively going to grab you by your top molecule and your
Uh-huh.
bottom molecule, and we into one long thread OU that would look
Wow.
like a noodle of spaghetti purportedly. Of course, to the best of our knowledge, this has never happened.
Right.
But who knows? Conjecture.
Yeah, who knows? Um, so was it your interest in black holes that was the thing that inspired you to get into astrophysics, astronomy, or was it broader? Is there some kind of origin story? I know you mentioned in the video, you Carl Sagan, but I'm just curious about, oh, was it I wanted to be Captain Kirk or Luke Skywalker as a personal hero?
Definitely not. No, no, not definitely not James Tiberius Kirk. Um, Um, no, I think, I would be wrong to say that growing up watching a lot of classic Trek repeats, seeing the rise of more modern Trek and Star Wars and all that, that didn't hurt. But I was always curious. And I remember falling in love with the sky kind of the first time I saw it. I thought stars were really cool. I have not lost that fascination. While the skies out here are not as good as elsewhere, still with our winter months and our cold nights, we've had some beautiful skies. And we're dealing with, letting the dogs out or dealing with some of the animals on the farm at night, I do enjoy seeing those stars. I have to, as always, give a lot of thanks to a lot of teachers. I would be a liar to say I really knew what physics was before 11th grade physics with a guy named Will Space, who really turned both my brother Ross and I onto physics. And yes, my high school physics teacher's name was Mr. Space. That's his real name. And again, great mentors thereafter. A lot of good teachers in undergrad. I'm pushing that idea. It did not go straight to black holes. We try and tell our students. I'm always saying, you follow the meandering of the river in so many ways. Try not to fight it that much. It doesn't go well. Where you try a lot of things. We try really express to our students that you ought to try a lot of things. If there are all these flavors of ice cream out there, there's probably a lot more that you don't like than if you do like. It might be a way of putting it. After playing around with a few different things that I was working with, I started playing around with radio astrophysics and looking at AGN, and I just thought this was really cool stuff. And it still remains a really big mystery as to what's going on there. And so it's not a well settled region of science. And even when I got in, I mean, if we're generous, that field's about 50 years old. In reality, at that time, it's probably closer to about 25 in terms of really meaningful modern work.
Wow. Okay. Did not know that. So I'm going to hold off on aliens and death for a few more minutes. I want to talk about traveling through space.
Sure.
And if circumstances were such that today, Bezos or Musk outfitted a spaceship for travel to a planet, a planet that we could populate comparable to Earth, what would that spaceship have to have in it? And how likely would it be, if we were two passengers on it, that we'd ever see a planet that we could actually establish a second civilization on?
Okay. So, a lot of important working details that I want to make sure I get right. So, one, we're not in this solar system, because if we want to get to a planet like Earth, we don't have another option here. As I'm oft to say, Mars is not Earth, full stop. And the idea of making it like Earth, as I'm quick to usually say, is not the wisest idea. You could spend that energy and effort elsewhere to make a much more workable situation. So we have to leave the solar system, is what I'm saying, if you want to get to an Earth-like planet. We do know that at this point, the closest star system to us, Proxima Centauri, a trinary system, 3 stars co-orbiting each other, it does have a terrestrial planet around it. I do not think that it is in the Goldilocks zone, but let's just say we haven't found them all and that there's one there for supposition. All right, so we have to cover, between friends, 4 light years. But we couldn't really easily do that right now. Now, humanity is impressive, so if we could somehow convince everyone to row in the same direction, that this was incredibly important, the easiest way to probably do this, because, man, you want redundancy. This was all, in many ways, this was worked out by Werner von Braun back in 1948, when he wrote Das Mars Project, which is easy German to translate to the Mars Project, where he works this out. And he's very clear in his writings, where he says something along the lines of, I want to once and for all dispel this idea of the single intrepid explorer and spacecraft doing this. And what he's saying is, this is lunacy, because what happens if your spacecraft blows up? Well, who? you're in trouble now. No, it should be a fleet. And the problem is, to make a fleet of such ships would be challenging at this point. Making one would be challenging. The best way that we get to your answer quickly is to build what is known as no Neil cylinder.
which is a pretty simple thing. Take a giant can. That's your spaceship. We're going to make a giant can. And when I mean giant, I mean big. How big? We're going to rotate this thing, and you're going to have a house inside this with land. It's going to be a big, solid thing. And spinning it is going to make you feel like down is gravity. We can point it towards a star, use LED lights at different times of day to simulate day and night in this place. It'll be weird. You can go outside and look up, and some not small distance away will be your neighbors up there, because you could walk all the way around, but same thing with Earth, not terribly different. And the idea of this is we'd be able to make it big. When you're trying to make these trips, size starts to really matter and scale rapidly. Because we can make big, thick walls that protect you, a lot of danger out there in space. We need to keep gravity going one way or another. We aren't certain what the minimum amount of gravity is for people, but we know 0G is super bad. You just start wasting away. It's very, very bad. It's why we don't just leave our astronauts up in space. We generally, if they've been up for any period of time, meet them with a wheelchair, because being back on Earth is challenging. And our astronauts in general work out every single day and not small periods of time to try to mitigate this wasting from a lack of gravity. So having gravity is really crucial, because to what you're looking for, this is not going to be a short trip. The whole, if we get on, are we getting off? Well, that depends. If we aren't using a kind of super future tech and we're keeping it to what we know we could realistically do today, let's say we just get enough energy to get this thing up to about 20% of the speed of light. That would be the fastest thing ever. And there'd be all kinds of questions about how do we stop when we get there. There are solutions. But okay, at 20% of the speed of light, what it means is 20% times 5 is 100%. In order to cover 1 light year at 20% of the speed of light, I need 5 years. Because our target is 4 light years away, that means we're going to need 20 years to get there. So for you and I, as I always say, everyone, long life, health, and happiness. Yeah, theoretically, we could probably walk on and walk out without trying to worry too much about old age. But we're already going pretty fast at that point. If we dial that back to 10% of the speed of light, just half that speed, then it's 10 years per light year. Now we're at a 40-year trip. Now it could be getting interesting and dicey, depending on how long we're going to live natural lives. And there's nothing to say that our health on such a ship would be better and or worse than what we have now. So there could be other complications that come in with this. We have to realize we've never done deep space travel ever. Being the Apollo missions are as far as we've gone, and that's just to moon. That's not really what we would classify as deep space. Truly deep space would be outside of our solar system and really getting into that. Right now, we call it kind of beyond Earth because we haven't been there yet. But that's kind of like saying this lake is big, that sea looks bigger. Wait till you find the ocean, my friend. Then you start really dealing with situations. In each of these, you have distinct challenges of scale. And so there's a lot that we don't know. To cut to the quick of your question, could humanity today get passengers there realistically? Not really, but you're not far off. It's not as far off as we might believe. It's a matter of motivation. We are, as you alluded to, with Jeff Bezos and Elon Musk, best billionaire fight I've seen in a while, because I'm cool with this. As long as you guys want to keep building science crafts and moving science forward, that is, I constantly complain, at least in the Renaissance, they were building stuff with their money that we still have today, works of art, works of architecture, and this stuff. Give us something long-term. Give us something meaningful to the plebs. And so that's a good thing. I say this sincerely. Again, if you look at von Braun, who ushered in the Saturn V, this is the Apollo space missions with the 80s and the space shuttle, that is a backwards move. It's lateral if I'm being super generous. Now, with the launch of the Space Launch System, we've just begun to get back to what we could do then. But to put a really succinct point on it, we can't do today what we were doing in the late 60s and early 70s. We're getting close to that. But we did it back then, and we can't do it right now. We just had 2 moon landers land sideways in the last month. Space is hard, and humans have barely begun learning this. Again, when we're talking about lakes and oceans, we're barely talking about rafts. We're talking about logs. that we're starting to figure out like a paddle helps. We've barely begun. We're at the most rudimentary stages of figuring out how to move across these bodies of water, these bodies of space, as it were. I think sometimes we think like these grand design ships. We are nowhere close to like Spanish galleons or some such thing, let alone like a modern aircraft carrier. Not guy with a log and a stick.
And there's also ethical questions, because if you did, you would probably be having people get involved in relationships, giving birth, and then you have children who did not choose to be born in space. And so now you have people you've made a decision for them that is largely irrevocable.
Yeah, and that kind of happens in the movie Passengers a bit. This is well explored in science fiction.
Yeah.
Because this is kind of a known. Even if, I mean, sometimes you'll have a ship that is going fast from the speed of light. It should get there in a reasonable period of time. It breaks down halfway there. And suddenly they're coasting for the next 200, 300 years, and you're stuck in this situation. Yeah, we talked about this before. There could be the idea of mission creep. There is the loss of focus as time goes on. We don't lose knowledge. We're going to have digital databases backed up to kingdom come. It's not like we're going to go, what is a word? That's never going to happen. But certainly a loss of focus can happen over time, as you alluded to. The people who got there could feel like, we don't even want this, and turn right back around if they had such a choice on this matter. I think I saw somewhere in chat, someone was saying, how long would it take to slow down?
Yeah.
Yeah, it's a great question. We talked about this off camera. Mark is discussing the idea that Carl was a big fan of this. The idea is you accelerate slowly. So you have a distance. For the first half of your distance, you accelerate at 1g. This gives us that idea of gravity that we can feel. We get around the gravity problem by constantly accelerating. And by doing this constant acceleration, we will get moving really fast. We're now going from non-relativistic to relativistic. I could do the math later on. It is not hard math, but it's not head math. The question is basically how long to get up to 10%. Then I have to do a bit more math to figure out what the total trip is. If you're accelerating at 1g, I can say it won't take you very long to get to 10%, because the whole idea of that approach is you get moving very rapidly towards the speed of light. It stacks very, very quickly on top of itself. It does not take a prolonged period of time. And again, the idea is you spend half your trip speeding up, and you spend the next half of your trip slowing down. So again, you start at rest and you end at rest, and you arrive at your location. I hope that's good enough, Mark. Again, as always, I'm happy to do that math later on. I couldn't do it in my head if I wanted to right now. Apologies.
Yes, thank you, Mark Granville. Aliens.
Put my head.
Kind of the same question with black holes. Do they? Well, no. Aliens. Should we be scared? And if what's feasible? We all have an idea in our head. Remarkably, the same idea. The same alien figure's been reproduced across film and in fiction again and again and again. And I'd love to hear your feeling about why that same hairless little creature,
little green men, little gray men, big black
right.
guys, no descript features,
big brains. Yeah, why that persists?
Not the big brains. No, we gotta go somewhere else. That's because we always think something from elsewhere is gonna be smarter than us, and that's probably our first mistake. They're probably just like you. We'll go to the first thing, which that one we understand pretty well, and that is your big old primate brain is great for doing a lot of things, but like every computer, sometimes it gets it wrong. And as again, I'm off to say to students, you quote someone else, it helps make you sound smarter. We'll go with Carl. Carl Sagan. He's always saying, why doesn't this ever happen in Central Park at noon? Why is it always at night? Why is it always in the middle of nowhere? And the answer is because it's your brain misfiring. It's an effect called pareidolia off the top of my head. And what it is, we know that with children, the first thing, and babies, just born babies, the way that they and everyone else identifies human first is you look at the eyes. This is why in horror, a lot of things will have one eye or more eyes, because if they're human-like, but the eyes are wrong, your brain it doesn't like that. And so the first thing we're looking for when you look out the dark window at night, little glint somewhere, your brain starts going, is that a pair of eyes? And then it starts filling in all the blanks for you. And by doing this, it has a big pair of kind of shiny eyes that your brain is filling in. You start trying to fill in the blanks of a nondescript shape. Why is it always gray or green? Those are the colors you're good at night. It's you. You are screwing it up. You are literally looking for something that's going bump in the night because that kept you alive for millions of years. It's just misfiring now. Something that would help you go, oh, crud, something's about to leap out of that bush and kill me. That's a good instinct to have that, right or wrong. And now we go, aliens. So it's like a lot of things, a defense mechanism that's misfiring. I think there's another part of your question. I apologize. More maybe just aliens at large. I mean, the Martians, the little green men, is an evolution of that. That's a discussion of Percival Lowell and some other things. You know, that's where the fascination grows with Mars. I always say, if you'll name me a Mars movie, I say, not The Martian, that's too easy these days. You can still prattle them off pretty quickly. There are lots of them. Name me a movie about Venus. And they exist, but they are few and far between. And a lot of them are actually from the former Soviet Union, because they did a lot more of the work towards the early Venera landings. That's Russian for Venus. And a lot of the information we have from Venus, especially the surface itself, comes from that Venera program. And it kind of, the space program was kind of bifurcated at some point, where the Russians just really had nothing but bad luck with Mars. They really just didn't do well. Whereas the Americans had a ton of success. And so Mars kind of became like an American planet, and Venus kind of became like the Soviet planet. I say this very softly because these are not things like anyone was declaring as policy or something, but these are kind of like soft thoughts that were in there. And so because of this, the Soviets kind of, that's where they went with some of their film at the time. And a lot of the Western film focused much more on Mars. It doesn't help that while Mars is not Earth, it's at least something that humans could inhabit. I call this flagism. I take this from Eddie Izzard, where he's like, if you're a country, you have a flag, no country. And the idea is, what's the first thing that humans did when they're landing on new lands? We're discovering things that humans have known for a long time. Flag. What happens when humans go to the moon? Flag. What happens when humans go to Mars? Flag. You can't do that on Venus. The idea of humans walking on the surface of Venus is absurd, because the environment, again, quote Carl, he talks about Earth and Venus, heaven and hell. Venus is the hottest planet in the solar system. The atmosphere is 100 times the density of Earth's. It's trying to melt you and crush you simultaneously. That's a lot of work to plant a flag. I don't imagine we'll really ever see humans walking on the surface of Venus unless we do heavy terraforming of Venus beforehand, or unless there's a really good reason that we don't send a robot.
All right. So trying to think, would I prefer spaghettification or melt?
Oh, Venus. Oh, that's not even a choice. The black hole is going to take time to kill you. Unless you kind of like drop me off right at a point where it's going to start snapping me to pieces. No, Venus is going to get that done like that. Again, perhaps slightly gruesome, but we all experienced it this last summer, the tragedy of the Titan's Gate submersible. This is exactly what's going to happen to you on the surface of Venus. You're just going to, and that's going to be fast. And so in that sense, I'd prefer not to feel it much. Maybe I'm alone in that column. Quick sounds better than long, at least for my discussion, which is the preferable death.
Okay.
It's not slow melting. Oh, I'm melting the Wicked Witch. No, it's going to be really pretty fast as far as I'm concerned.
All right. So melting, quick beats long. I got it. All right. So before we leave this whole Russia's embrace of Venus in film, what are their aliens look different? Not a lot. But what did their aliens look like? Were there any significant differences in representation of alien life?
Not that I can remember off the top of my
Okay.
head. It's a fantastic question. I would need to go and look. The honest answer generally is back in the day, I tend to say to my students, which is more accurate, Star Trek or Star Wars? And I go with Star Trek because they had a lower budget. And so it's just people in costumes and face paint and stuff of this nature. Whereas Star Wars, we have all these exotic creatures
Yeah, yeah.
and other things. And using what we tend to call either the Copernican principle or the principle of mediocrity, the idea is that you should be average. And if life on Earth is average, it should be probably very similar to life elsewhere. We look here on Earth and we see that having 5 major bodily appendages, that's your head, 2 arms, and 2 legs, seems to be a winner. We see it everywhere. There are exceptions, go to insects and spiders, but the big stuff, we don't tend to see stuff that violates that body plan.
Right.
And so that doesn't mean anything on its own. But if we apply that principle of mediocrity to that, if we say, okay, if it ain't broke, don't fix it, then we probably expect it to be much similar to you. As I would say, if you're a lower gravity planet, probably taller. This is better for moving around. If you're in a higher gravity planet, smaller, it's easier to sometimes think about this. If you're a really tall person on a high gravity planet, a fall might kill you. Keep yourself closer to the floor.
Okay.
Think dwarfs,
Think dwarfs.
as in like Tolkien dwarf.
Has there ever been in anything you've seen a representative female alien in a film or
Oh,
like
for
something?
sure. Lots of them.
Yeah.
I mean, just go with classic 90s schlock. Species 2, Species 3.
Oh, sure, right. I remember that. Okay.
Just right off the top of my head. I would need to think.
Yeah.
I mean, there are tons more. Certainly in Star Trek, the Borg Queen. I mean, in theory, if we classify her as female, I mean, she's certainly played by a human female. I mean, she's running one of the most powerful empires in the galactic, in galaxy, I suppose. I think in general, this goes to science fiction, where generally you have very progressive minds, not always. And there's a lot of push for equality. I mean, again, low-hanging fruit. You go with the first interracial kiss between William Shatner and Nichelle Williams, or
Right. I remember
Nichelle
that.
Nichols or whatever it is. I apologize. I'm so bad with names.
Yeah, I remember that.
But
Okay.
that was a big thing. I mean, it's the big part of, to really put the important part. We're just coming out of Black History Month on that. I think it's Nichelle Nichols. That's going to drive me nutty. Was going to quit because she really didn't think she was getting representation, both as an African-American woman and as a woman on this. And she has this really kind of fate-twisting interaction with Martin Luther King Jr., who says, like, oh, I love you on that. I'm such a Trekkie. And that's part of her staying on and becoming just a historical piece of our entertainment. I think in general in sci-fi, more so than in most genres I can think of, especially going farther back, there's been a lot of depiction, I mean, of women in positive roles. I mean, in the film class you mentioned, we tend to start with Plan 9 from Outer Space? That's because it's so bad. And again, led by a woman in many ways in that cast.
Thank you to Joanne Gemma, who I was looking it up too.
Thank you.
Nichelle Nichols, Lieutenant Uhura, died in 1989, evidently.
No, she lived until recently.
Oh, 80, I'm sorry, died at 89.
Yes,
in
that's
Silver City, New Mexico.
Yeah, thank
July
you.
31st.
I wish I had my better half. My wife knows everybody's name.
There you go. Thank you. So let me amend my question. In terms of people who say they have seen little green men, has anyone said they've ever seen a little green woman?
I don't think so, but again, it goes back to the whole idea is they're nondescript. Most of the time, as far as I know, they're not really talking about gender. It's like, I saw a thing. I think we just go to little green men has become kind of the go-to term, like we say Kleenex or Q-tip. It's become kind of a brand name thing versus what it's actually called. But no, in the sense of what we're misseeing, it's really just that. As I'm quick to say to my students at the start of every class where we talk about this, I'm like, look, I wish I didn't have to say what I'm going to say, but here it is. At this time, there is no evidence whatsoever that anyone has made public in any manner that can tell us that aliens have visited and extraterrestrial intelligences have now or ever visited the planet. And there are lots of loopholes that you can drive buses through in that statement, like that you don't know they're here. And that's not unreasonable. If I am, again, I think it's Arthur C. Clarke who's saying, if any sufficiently advanced technology will appear as magic, it's that idea. If I can cross the stars, I have technology you're going to struggle to even think about, and being unnoticed by you would have been very easy up until the last century, like really
Mm-hmm.
until you started building a space program. That was dead simple for me. No cloaking devices, no, just stay on the far side of the moon. You didn't see that until the mid 1960s.
Mm-hmm. So Fox Mulder would be deeply disappointed by your answer.
Again, as I say, I wish it were different. It'd be way cooler. Say, hey, look, aliens. That sounds like a more interesting. But both biology and astronomy would be enthralled, because we don't know if life out there is going to be not just looking like us, but if there's even genetic choices that can be there. If DNA is the only answer, if having ACTG as our genetic alphabet is the only answer. We don't know these things. Biology and astronomy are either woefully incomplete or really good, and we don't know because of these lacks of information.
Mm-hmm. One thing I just want to say, in case there are undergraduates, or maybe this is a course that's available to graduate students too, I don't actually know the answer, is that you team teach a course with Rebecca Romanow of the Harrington School of Communications on, well, why don't you give the formal name of it? So, because I'm going to butcher
It
it.
is Science and Science Fiction in Cinema. And it is just great. I've wanted to teach this class for years. We've done it once, and Rebecca is amazing. I could sing her praises all day long. She is so well read and so well versed. It's probably one of the most fun classes that I've ever taught, because I felt like a student when she's teaching. And I was like, ooh, as we're doing it. So all the more reason. It was fantastic. We focused mostly on film in this last run, with some literature along with it. I think on the next iteration, we're going to be doing a lot of a focus on television. And I've been floating the idea of doing old and new, as in looking at, you've got plenty of series, The Twilight Zone, The Outer Limits, Star Trek, Doctor Who, the list goes on and on, where we have like an older version and a more newer version. And we can kind of see what changes in between them. As I like to argue, the modern audience is much more well educated than prior audiences were. And you used to be able to get away just gobbledygook coming out of your mouth. Oh, the quantum this, reverse the polarity of the neutron flow, is the classic Doctor Who moment where there is no polarity for neutrons. Now more of the audience kind of understands this stuff. You have shows like Rick and Morty, shows like Futurama, where they're actually working really hard. These are animated shows in theory. They're supposed to be funny, where they're really making sure they put in the effort. In Rick and Morty, there's many ways you can move through dimensions and multiverses, for example, and they chose a particular one and a theory of how you do that, and they've stuck to it, because they've never gone outside what you can do in that theory. And when they have little things like, they had a robot ghost fall through the floor recently, I was like, oh, thank God. It drove me nuts growing up watching the movies. Okay, so let me get this straight. The ghost can walk through the walls, but the ghost walks up the stairs and doesn't fall to the floor. What is magic about those things? Those are the little things that I mean that nowadays more and more people are queuing in on.
Yeah.
And they like that, because I say, entertainment is about slightly divorcing yourself from reality, not completely divorcing yourself. There has to be a lot that you're like, that's familiar, but ooh, that's new, that's cool. I say, Harry Potter, it's your world, magic. Star Trek, it's your galaxy, force. Otherwise, it's kind of rounded beyond that.
That's really interesting. So basically, yes, it's outer space, but even in outer space, there are limits to the suspension of disbelief.
I think a lot of people understand with Star Wars, it's a Western. It's a spaghetti Western. George Lucas was stealing so heavily from Kurosawa and so much of his childhood with spaghetti westerns.
Mhm.
If you hadn't thought about that, go back and watch A New Hope and go, this is super duper a western.
Yeah, I didn't know that. I know that I think Lucas has said Star Wars borrows heavily from King Arthurian legend.
That too.
Yeah, going back to the old, which, you know, I mean, I think about the original Twilight Zone. I mean, that holds up. It's still freaky.
Oh, it's great.
A wonderful lesson in kind of short, you know, single effect story development in the vein of Edgar Allan Poe. You know, like
Yeah.
you know, you get to
But
that.
that was Rod Sterling. That was Rod Sterling. Again, for his time, he was a rabble rouser. He got a lot of flack for that. He was pushing very progressive ideas, but humanism, as I would say a lot of times. And that's kind of this linking thing between people like Sterling and Roddenberry. Lucas, to a degree, less so. He's doing a bit of his own thing. He was more interested in the art than a lot of the science fiction that was kind of driving it. But again, in all of this, there's a lot of linkage.
All right, we have a question from Josh that I want to make sure I get to before we get to death. What are your thoughts on using gravitational propulsion to propel a spacecraft?
Well, what's driving our gravity drive would be my first question. At this point, we don't really have a mechanism. So to me, my mind goes to like an Alcubierre drive, which is, for anyone not in the know, a warp drive. So a Mexican physicist, Alcubierre, came up with, within the working knowledge of relativity that we have now, a way of moving through space faster than the speed of light. This is important because we skipped over before in our discussion that as you move closer and closer traditionally to the speed of light, you start encountering relativistic effects. And namely, we said this is time dilation, and this is what makes it a one-way trip, which kind of sucks. The basic idea is if I move fast enough, time is going to stop for me. I can cover any distance I want, but all my friends back home have lived their lives and died. And so it's very sad. And that would make bad entertainment, which is why we don't normally see that. It has been well covered in sci-fi. But that's where the magic of the warp drive comes in the sense that we can arrive and everyone's there and we can quickly move between things. One, warp isn't nearly fast enough, but we won't step on that in that landmine right now. But what it is, we go back to what I was saying before. I said like Rick and Morty and Futurama, for example. Futurama nailed this like 20 years ago when they said, you know, the ship doesn't push itself through the universe, it pushes the universe around itself. And that is the answer. You can't move faster than the speed of light without encountering those relativistic effects, but space can move around you. And that's effectively what a warp drive is. You stay still, the universe moves. And it's a kind of a hack to move around this. We have no idea how to really make that work. And this is the great trinity of mathematics, physics, and engineering, where the mathematicians give us some of the tools so the physicists can go, okay, what can we do with those? We build our theories, and we go, engineers, yes, go build this. And they're like, how? And so, yeah, it's one thing to say, yes, warp drives could exist, and the engineers go, wonderful, how do we build one? And that's kind of where we are now. If we can take it farther, or if we can move that to an email, I can probably dig more deeply in that. There are a lot of different ways to do that. Again, in science fiction, we can have powerful enough gravitational waves to ride that like a surfboard under the right conditions. It really, when you're talking about gravitational drive, you're kind of talking about a whole host of possible propulsion mechanisms. Just like if we say chemical rockets, okay, anything that throws chemicals out the back by burning it, we're probably gonna call that a chemical rocket.
All right.
So, Josh, I hope that was good. Otherwise, write to me. I'm happy to try and do better.
So in the 5 minutes that we have left, death in space, and this is a two-parter. Talk about the worst death in space if you're in your spaceship or you're out of your spaceship without your spacesuit on. Because when we talked about this prior to this presentation, that was quite the interesting, that would be quite the interesting last experience to have in one's life.
Yes. So to fill in the blank there, the basic idea is if I toss you out of an airlock just wearing your civilian clothes, you're not going to die instantly, and you're certainly not going to turn into a popsicle immediately. For the I'm in the spacecraft, and we'll go with stuff that's happened.
Okay.
No one, again, we had that conversation. It's a careful one. Again, lots of big loopholes, but as far as we know, there's that first careful statement. As far as we know, no one has technically died in space. They've all been within the atmosphere, and we treat those just the same as a plane crash. So, on a technicality, no one that we're aware of, keyword they're aware of, has died in space. However, there have been close calls. For the in the spacecraft, it's again a delicate conversation that I don't have the time to give the nuance to. But while we have the idea that space is cold, it's actually quite warm. And it is a big problem to try and keep you cool while in space. And that will link these two ideas together, where both of these are going to be death by heat in a way. Inside my spacecraft, if I cannot properly get rid of all that heat that I'm gathering, I will cook. And that sounds like a very slow, unpleasant way for me to go. Because it's not just going to be crank up the temperature immediately. This is going to be me just getting slowly warmer and warmer and warmer. And that's not going to be fun. Simultaneously, if I'm outside, and again, I'm terrible with names, this happened to, I believe this was on the first spacewalk with a cosmonaut. Well, same thing. The first spacewalk was with this cosmonaut. It's not going to come to me. Again, so bad with names. I apologize. But he was getting hot because he's out there, and they didn't have a good enough system yet to really keep him cool. And so he's sweating profusely to try to keep himself cool. And he starts to fill up his spacesuit with his own fluids. And so he was getting close to drowning in his own perspiration. And again, he could barely see because it's all fogging up here. He had kind of swollen up because of pressure imbalances. And he was struggling to get into. He lived. But this was I think about something and saying, you know, these guys and woman, Valentina Tereshkova, first woman in space. Wow. I mean, and you look at some of them and they are just calm under fire. I'd like to think that I could try, but that is a gnarly circumstance I would not want to find myself in. No, thank you. I'll be like 16th, not first. Yeah, you guys go first.
Wow. And then without the spacesuit, how are we dying?
So again, it's a bit of a race to the finish line. If I'm left out in space, what's going to win? Probably hypoxia pretty quickly. I mean, you're going to want to breathe out to begin with. That's going to help prevent you from wanting to space. We know that space abhors a vacuum. You're greedy. You're trying to keep your air to yourself. Well, give it to the others. And so we want to kind of pull that out of you. You will start getting colder before you're going to get warmer. So again, it's delicate there. Shock is definitely going to be a big part of this because your brain's going to be involved in, oh God, this is not good, because you'll understand if you're in that situation, you're going to know whether or not you might survive this. And so panic and shock might come to the rescue and just knock you out. But probably exposure, it's probably hypoxia, because we're going to be pulling that out of you. As we said, because we're not aware of anyone who's gone through this. We do know, for example, there was a NASA engineer, we mentioned this again earlier when we were talking, who was in a vacuum chamber that accidentally was depressurized, and he survived. That was a kind of, we didn't think that was going to go that well. And suddenly our knowledge expanded. As I'm off to say, I'm a martial artist on the side, and as a physicist and a martial artist, I say, and a scientist, I've ruined movies for myself forever. But human beings are both very fragile if I know how to hit you or where to hit you or what to hit you with, and simultaneously incredibly robust, can survive just enormous pressures and temperatures. We see humans that survive things sometimes that just we go, how? So it's hard to say until we get there. It's not the insta death that people think it is, and that's important. We see in cinema the kind of instantaneous freezing that happens, and that again, your skin will freeze pretty quickly. The thin layer of perspiration here, and that might show as a little bit of frost. But you, as a we're going to hit something and freeze off instantaneously, that's not going to happen. It's going to take you hours to get that cold.
Yeah, so you're going to have an oblique moment before you.
You're going to have some time with thoughts.
What a note to end on.
How did I find myself here? Well, I should have inspected my contract more closely.
Well, thank you for answering all the questions of the universe today. I think this is a first. So yes, thank you, Professor Gobeille. And thanks to everyone who joined us today. As mentioned, within the next few days, you will receive an email with a link to today's recording and quite an extensive list of recommendations for those who would like to read, listen, or view more. We hope you'll join us on April 3rd as we continue our celebration of the 75th anniversary of the College of Arts and Sciences with a discussion about quantum computing with Professor Leonard Kahn. Thank you again, everyone, and enjoy the rest of your day.
Thank you all.